Hello everyone, my name is Aarohi and welcome to my channel. So guys, in my today's video I'll explain you about EfficientDets. So EfficientDet are the models developed by Google in 2020 and these models are used for object detection. So guys, on my channel I have already explained you different models. By using them we can perform object detection, right? So we have discussed about faster RCNN, we have talked about, I've shown you the implementation of single shot detectors, and then we have seen the practical implementation of YOLO, V3, V4, V5. So we have worked on various object detection models. So if we already have learned so many object detection models, then what is the benefit of learning EfficientDet, right? How EfficientDet is better than other models. So like we'll talk about all these things, how EfficientDets are better than other models, right? And what is the layer architecture of EfficientDet, and what is the main intuition behind this EfficientDet. All these things we are going to cover in a today's class. So let's begin. So guys, why EfficientDet? The very first thing is, if we are using any algorithm, then why we are using that algorithm? You should know this thing before using any algorithm, right? So why one should use this EfficientDet model? Because EfficientDet models are smaller in size. So if your model is smaller in size, what will be the benefit of that? Smaller size means it require less resources. Less resources means it will consume less memory. You can work on less memory CPU and less memory GPUs, right? And computation will be less, right? So if your model is smaller, ultimately processing will be fast, right? Fast processing means high efficiency, computation cost will be less, right? And with this we are also getting higher accuracy. Means our model is small, our model is processing fast, and we are getting high accuracy as compared to the previous object detection models. So this is what we want in whenever we work on any algorithm, this is what we want higher accuracy, and we want smaller model, because nowadays what we want is there are different devices on which we want to run our application. Let's suppose you want to build a mobile application which uses deep learning models. So if you want to run your this algorithm on mobile, then your this model should be smaller, because the resources over there on your mobile, the resources over there and the resources which you are using on your laptop will be different, right? So you need a smaller model for your phone. So over there, for that you need smaller models, right? So we can use EfficientDets everywhere and we are getting high accuracy. Now let's talk about the other object detection models and EfficientDets in detail. Okay, so when we start talking about object detection, so the task is divided into three parts. Every object detector works in three parts. The first part is a backbone, and the second is a feature network, and third is a detection head. Let me explain you this in brief, and then I'll explain you the EfficientDet model. Let's consider this image. So this first block, this is a backbone. I have told you, like, every object detector have three components. First is backbone, second is feature network, and third is detection head. So this is the backbone, and this thing, this small rectangle, and in that we have these colorful rectangles inside it. So this C means convolutional layer, R means ReLU, P means pooling, and D means dropout. So I am just showing you a random convolutional neural network for a backbone task. So why we use backbone? So we use backbone in object detection models for extracting features, right? So for example, this is our network, and this is the input we are giving to the network. And from the initial layers, from the very early layers, you will get very low level features, because these are the initial layers and our model hadn't performed, hadn't processed it well in the initial stages. So we are getting very low resolution features, means low quality features, low quality features. Okay, and from the mid of your model you will get middle level features. Okay, and from the very last layer of your network you get high level feature. High level feature simply means the features which contain more information. The resolution of those, the resolution over here, the resolution of the features which we obtain from here, the resolution will be very low, but those features contain very important information, because we are getting those features from the very last layers of our network after lots of processing, right? And the features which are available at the initial stage, the features which are low level feature, means where the information, we are not getting much information, right? Over here we are getting low level features, but the resolution of the features would be high. Okay, I hope this is clear, right? So now backbone is used to extract features, and normally in most of the object detection models we use ResNet as a backbone, or we use VGG16 for backbone. We use these two models for feature extraction, right? And once you get the high level features from this image, these are the high level features we get, right? Final stage. After that, these high level features, we send these features to the feature network, the second component, feature network of object detector. The task of this feature network is to combine all the features and send those combined feature to the detection head over here. Okay, and what detection head does, what we do in object detection, we want to plot the bounding box around the object, and then we want to put a name of that object. So we need a classifier and we need a code for plotting that bounding box, right? So this softmax classifier, let's say the softmax classifier is telling us about it will give you the name of the class, and this regressor over here, this will give you this will plot a bounding box on your object, right? So this is how normal object detector work. And one more thing I want to add over here, when we talk about this feature network, most of the time we use feature pyramid network, FPN, as a feature network which collect all the feature, and then it send those fused feature to the detector for further work, which I've just told you. Now what this FPN is, FPN simply means multi-scale network, right? I'll explain you a little bit more about FPN, but right now just understand we use FPN because FPN, using FPN we can capture multi-scale features. Okay, so this is how normal network work, normal object detector work. Normal object detector use ResNet 50 or VGG16 for backbone, FPN for this feature network, and over here detection. Okay, now let's see how EfficientDet work. Again, EfficientDet is a object detection network, and we are going to have three components over here also. We are going to have backbone, we are going to have feature network, and we are going to have this detection head where we will perform classification and the bounding box plotting part, right? But instead of using that ResNet 50 or VGG16, they are using EfficientNet as a backbone. So guys, if you will check my previous videos, and in those videos I have recently made few videos on EfficientNet, and I have explained you that EfficientNet is a image classification network by Google. So Google is using their EfficientNet their model here, EfficientNet, because EfficientNet is again a lightweight model due to the scaling part, right? So if you want to know more about EfficientNet, then you can check my channel. Over there I have explained in detail what EfficientNet is. So right now just understand that for object detection and for this backbone part, EfficientDet, Google is using EfficientNet as a backbone. Okay, so the task of backbone is similar. We are extracting feature, but instead of using ResNet 50 or VGC 16 or other network, they are using EfficientNet. Okay, and then next is feature network, where we will combine all the features, right? Over here they are not using FPN. What they are using is they are using BiFPN. BiFPN simply means bidirectional feature pyramid network. Now why they are using BiFPN, why they are not using FPN like other networks, right? Like other object detection models which we have discussed earlier, why they are not using FPN, why they use this BiFPN? Now to make you understand this, let me show you this image. Okay, just check this image. So this is the input image. Suppose this input image you are giving to your network, and I have told you that FPN is a multi-scale network. It will capture features from multiple scales. Okay, and you can see over here we are able to capture even a small objects, right? In next image you can see over here on this area we are not capturing anything, but over here we were able to capture all the small tiny objects, but in next scale we are not able to capture those. And if you'll see over here, even here you can see we are capturing even very less data. Over here we basically the tiny objects are not getting captured over here, and over here, and see over here. When you compare all these 5 different scales, these are the 5 different scales. So FPN starts scaling from P3 to P7, P3, P4, P5, P6, P7. So we have 5 different scales from where we detect objects. So these are the output from 5 different scales. Okay, now so the P3, guys, this numbering is wrong. This is P3. Okay, so at P3 scale you can see that we are detecting smaller object, and P4 scale we are not able to get very smaller object, but still we are capturing some small objects, and in others you can see. And P7 is the the final scaling, where we are only capturing the objects which are larger in size. So this is how FPN work, multi-scale network. And in normal object detection model, what FPN does is FPN give importance to all the input features equally, right? What FPN does, FPN gives importance to all the features. And how we are getting all the features? We are getting all the features are of different resolutions, because we are using different scaling, right? So what FPN does, FPN give equal importance to all the features, and all those features are of different resolutions. And obviously all the features are not equally important, right? All the features are not equally contributing to the output features. So in normal FPN, the problem here is this FPN is giving equal importance to all the features, and all those features are of different resolutions, and it is quite obvious that all the input features are not equally contributing to get the output features, right? So this is how normal FPN work. But in EfficientDet, they worked on this problem, like the problem which I've just said you, like this EfficientDet team, they don't want to use all the features, right? What they want is they want to use only those features which are more important for the network, right? And how they does that, they they provide, you know, some weight value to all the input features, and they started learning about the importance of each feature, and finally the features which are more important, they are working on those and they are leaving the other. So this is what BiFPN does. So this is an improvement, right? So we are basically segregating the features over here after knowing the importance of all the features. So now we have refined features. Now we have the features which are more useful for our network. For, you know, when our network wants to perform the detection, we are giving the, you know, good quality features to our this detection head over here, because we have refined the feature, we have segregated the features. They use this BiFPN, and they have they provided some weight value to each input feature, and they tried to know about the importance of each feature, and the features which are more important, they are working on them. So after that we are having a fully connected layer, and we have a softmax classifier which will tell us the name of the object, and this regressor will plot a bounding box in it. So this is how EfficientDet work, right? This is the basic idea. I've gave you the basic idea, and this is the picture which I have created. And guys, if you check the picture, this is the picture from the architecture, from the paper, and this kind of image you'll see over here. And this is the backbone, this is the backbone which I have shown you over here. And after that, this is a BiFPN feature pyramid network. Okay, so you can see that this task is repeated 2 more times, so they repeatedly use BiFPN. So you can see arrows downward here, and you can see arrows upward over here. So this is a top down approach, and this is a bottom up approach. So BiFPN use top down and bottom up approach so that data flow in both the directions, and they repeat this process for 2 or 3 times, and then they get the fused features and they pass those features over here, right? And over here we will know the class name and the bounding box. So this kind of image you will get, and to simplify this, I have created this image for you guys, right? So now we have the basic idea about EfficientDet. Now what next? So guys, model scaling. The another idea behind this EfficientDet is model scaling, and this model scaling, they used model scaling in EfficientNets. And if you want to learn about how resolution scaling is beneficial, how depth scaling is beneficial, and how width scaling is beneficial, you can check my EfficientNet video. In that video I have explained all these things in detail, right? What is the benefit and how these scalings are helpful, all these things I have explained in that. So over here we are just going to discuss like the model scaling part which they have implemented in EfficientNet, and they have seen the good results, so they have introduced that scaling idea over here also. And they want to scale the backbone, they want to scale the feature network, and they want to scale the detection network, the detection head. They want to scale all these 3 networks, right? What all 3 networks? They want to scale the backbone, they want to scale this BiFPN, and they want to scale this detection head, right? And all the 3 parameters they want to scale. They want to do resolution scaling, depth scaling, and width scaling, right? So in short, we can say resolution scaling simply means increase the image size. So if your image size is increased, you will be able to capture more detail, more features, you can get more fine-grained features from there. And if your image is of bigger size, then obviously to handle that data you need a deeper network, right, which is depth scaling. And why you need this depth scaling, why you need more number of layers in your network? Because your image is of higher size, information is going to be bigger now, number of features are going to be more, so to handle that we need a deeper network. And why we need width scaling, why we need more number of channels? Because we want to capture more fine-grained features. So that is why these things are related. Okay, So model scaling will also be implemented in EfficientDet, and we'll do model scaling for backbone, we'll do model scaling for FPN this feature network, and we'll do this model scaling for our detection network. Okay. After that, now when we talk about model scaling, so how we scale the model? So what the people explained, that they said that this scaling should be in a balanced way, means resolution, height and width should be scaled in a balanced way. Okay, so how we can scale the height, width and this depth in a balanced way? For that, there is a concept with the name of this compound scaling. I'm going to discuss that in a few next minutes. So before that, in EfficientNets we have different variant of EfficientNets, right? B0 to B7. In the same way, in EfficientDets we also have different variants of EfficientDets, D0 to D7. D0 is the base network, and once you get the D0 network, baseline network, and then we'll apply a compound scaling on it, and applying a compound scaling will get the further networks D1, D2 up to D7, right? And when we want to do compound scaling, we need a value of phi. So guys, again, if you have seen my EfficientNet videos, over there also I have discussed about this phi. So the value of phi we define, and the other things they have already defined. Let me show you. So come here, this compound scaling. So this is the formula of compound scaling: alpha, beta and gamma. Alpha is depth, beta is width of the network, and this gamma is resolution of the image. And this phi over here, this phi is a value which we provide, and alpha, beta, gamma already given, we will use those values. And you can see over here the value of alpha is 1.2, value of beta is 1.1, and value of gamma is 1.15. These are the fixed values. You have to use these values. The value which will change, that value will be the value of phi, right? And let's suppose you have a D0 network now, efficient D0 baseline network you have, and you want to create a D1 network now. Then the value of phi would be 1, right? And if you want to generate a D2 network, then the value of phi will be 2. Okay, you can see over here. So we have implemented this formula, right? So you can see here 1.2, what is 1.2? 1.2 is a value of alpha, and 1.1 is a value of beta. And this 3 simply means I want to build a D3 model, and that's why I'm giving this 3 as a value of phi, and over here also. In the same way, if you want to build this D6 model, then the value of phi would be D6, right? So guys, you can see here D0 is for value of phi 0 when you want to build D0 network. In the same way, these are the different values you need when you want to build different networks. And for D7, guys, you can see over here, for D7 we are not using the value of phi equals to 7. You're not using that. Why? Because over here, if you will use the value of phi equals to 7, then you have to make few changes in batch size, and there are other there are some places in your code where you need to make the changes. So this author just expanded the value of D6 into the D7, means we will use the value of phi 6 in D7 model, but we'll change the image resolution, right? So in D7 and in D6 there is only one difference, that is a resolution of the image. Let me show you through the chart. Okay, so we have a chart over here. You can see here D0 to D7 model. So in D0 model, the input size of images resolution we are using is 512, and over here in D1 model the input resolution size increased to 640. We are performing the scaling, right? And over here also you can see number of channels are increasing. We are doing everything over here, right? But in D6, see D6, we have an image of size 1408, and in D7 we are using the image size of 1536. Rest of the things are similar, right? See, the number of channels are similar, backbone is similar, the number of classes are similar, right? Everything is similar. The value of 5 will be 6 over here. The only change is the image size, right? So remember, whenever you want to work on D7, if you use the value of 5 as 7, you will get memory issues. So to resolve those issues, you can directly use the value of 5, right? And you can only, scale your model, scale the resolution over here. Okay, so now these are the different scaling formula. So I have told you, like, we want to scale the input image, we want to scale the the feature network, we want to scale the detection network. So these are the different formulas we are using. So let's talk about this input image resolution formula. So what is this 512? Because the initial size of image in EfficientDet is 512. Remember, we are starting the image size from 512. So that's why I've written 512 plus 5 simply means if you are building a D3 model, then the value of 5 will be 3. If you are building a D5 model, then the value of 5 will be 5. Okay. Dot 128. Now what this 128 is, guys, remember in FPN I have told you we are using different scales which starts from P3 and which goes up to P7, right? So we have scaling up to 7. So 2 raised to the power 7 equals to 128. So that's why we are writing this over here. In the same way, these are the two different formulas which we use for scaling our different networks. Okay, now let me show you the performance, right? So in the very beginning I have told you, like, I'll show you the performance comparison with few models. So over here we are discussing that. So you can see over here in this particular slide I'm comparing this D0, the baseline network of EfficientDet, with YOLO V3, and this in this graph we are discussing about the model size. So the number of parameters which YOLO V3 use is 65 million, and the number of parameters which EfficientDet use is 4 million. You can see the huge difference over here, right? So you'll get the similar accuracy with both the models, but you can see the model size of YOLO 3 is, we are using lots of parameters in it, but we are using very few parameters in EfficientDet. Now the number of parameters are less over here. What will happen with that if you have number of parameters less, fewer parameters? Computation will be less, right? And you need less resources, speed will be more, and even we are getting higher, almost equal accuracy with both the models, right? Now let's see over here. Now let's see how much training time both the model takes. So YOLO V3 took 24.5 minutes and EfficientDet model took 18.3 minutes. So guys, these are the initial over here we can see that this is not a very huge difference, but if you'll go for the further models, over there you can see more difference, right? So this is how you can see the comparison of these models, and over here also you can see the different comparisons. You can see that this D0, D1, D2, D3, so this model is using very fewer parameters, and it is giving us very accuracy with EfficientDet is more as compared to other models, right? And okay guys, that's it, I think. Yes, so this is what EfficientDets are. So EfficientDets are smaller in size, they give us high accuracy, and we can run this code with less resources, right? So in my next video I'll show you how to use pre-trained models of EfficientDets, and then I'll show you how to use EfficientDets on your custom dataset. So guys, that's it. Thank you for watching, and I hope you like my video. Thank you for watching.